apply discrete time Fourier transform for network analysis. Oh, yeah. This one will be fine. So, I have a network. My network is, I have an AC source with RMS 10 volts and frequency 300 hertz. Yes. Its powers rectifier. Rectifier. Can you please take an attention? If you think that someone published analysis of or such task solved, I have a very bad news for you. Zero, nothing, nunca, none. Here is my rectifier. From my rectifier, coil 100 millihenry. With series resistance, it's a coil resistance of 20.3 ohms. Capacitor 5 microfarads. Next, coupled coils with metal inductance 10 millihenry. This resistor 220 ohm. self parameters of the coil. Self of the coil for 9.3 millihenry, 6.7. Self 9.3. It's in millihenry and 647 ohms. This part 7.6 ohm. It's a self resistance internal and self inductance 42.53. Millihenry. Okay, I can now just be grounded. This is grounded. Your task is to solve this network. Find voltages and current. How will you do it? Any ideas? Check for yeah, 10 volts. Second TV will go on. Here, I and my network. Ideal sine source, powering and rectifier. Yellow line is a voltage at this point. Any ideas how to solve this network? It is neither DC, neither AC network. It can be solved like this. It's outside of your comfort box. It's not DC network and it's not AC network. What shall we do? First, we do have techniques only for good techniques for DC and AC network. Our first step is to decompose. Assume this voltage, non-sinusoidal voltage powering our network as a signal. And assume we have our signal here. What will be mass description for signal of rectifier? If RMS for this source is 10 volts, ideas? And what you've done on electrotechnics theory, we can use very simple thing. We need a voltage will be something like this. Our signal is an absolute value of it. Here is output of rectifier. You should know it. It's basics of electronics. So we need source of 10 square roots of sine double P divided by period time for time starting from 0 and up to period. Yeah? In reality, I'm already aiming at discrete time Fourier transform. I need a table of values. I will need table number 1, 2, and my signal. Now I'll show how it can be done. 1 second, I only need yeah, fine. This is fine. Why? I will do it in syllab environment. It's very easy to understand. So I need to set number of points. To make my life better, let's say, and I will have my table with a step of half degree. I will have 720 points per period. E is 10 multiplied by SQRT of 2 SQRT. Yeah. Now I need to fill my signal table. So multiplied by 0. I created an empty array of 720 points for I starting from 1 to number of points. Equals to A multiplied by sine of I minus 1, y minus 1, because yellow line starts from the 0, multiplied by 2 multiplied by PE and divided. Clear? What I'm doing? What I will get? I will test myself. I will get at this point same value of sine. I'm just checking. Sorry. What? Oh yeah, I need values of omega t. Yeah. So x equals to SE at this point. Equals to would be nice to have it this one will be in radians. To get it in degrees, I should multiply by 180 and divide by p, yeah? So I will need to write here 180. And here will be x values. Let's check. Will we get a nice chart of sine? What will be name for this? 25. Okay. Let's take a look. Where is my... oh, sorry. Sorry. One tiny mistake. I need to say what p is a constant. Oh, I don't know x value because x values. Oh, it's a chart of sine, yeah? From 0 to 360 degrees. Now I need to make a chart of rectifier. That means absolute value of yes. Can you believe what it's a voltage of rectifier? Yes, positive only. Let's magnify it. What's the value of this point? Wait, I don't need to. Can I take value? I don't know why. Okay, 14.1. Let's get it on a scope. Scope. .1, yeah? What is at the cross point? .0. You see cross point? At 14.0. Okay, we can live with this. What will be our next step? Ideas? What can we do next? We need to perform Fourier transform on it. We need to find components of it. We need to decompose it into DC component and AC component. I don't have a space. We need to perform a DFT on signal. Number of harmonics. Let's say 25. Do I have already? Oh! I can copy from myself. DFT. Time for DFT. Only one moment. Signal. Okay, what's going on here? Remember my formulas I wrote previous lesson. CK 2 divided by n, somewhere to change from 1 to number of harmonics, value of signal, cosine of pi minus 1, double p divided by n. And same for sine. Formulas of discrete time Fourier transform. Changing k, number of harmonics, from 1 to no, I think, okay, I will try 25. So from 1 to number of harmonics. For each harmonic, here is my sum. I wrote this one. Sum and 2 divided by number of points. Okay, it is. Last one is a DC component. This part is for let's try to see what I got. Chart we already saw. What about here are values of my harmonics. Second, first, nothing, second, fourth, and so on. This is cosine component, and I don't have C zeros. Because my rectifier is ideal, I don't have a sine component. If it would be a controlled rectifier, also sine component would present. But here are only cosines. Here is composition of my signal. I would like to check how can I check what Fourier transform performed correctly? Perform an inverse Fourier transform. If it will yield the same result as original signal, so it works correctly. Maybe I don't need this.
Do I have? Good check. Yeah. Look what I got here. Figure. I can copy from myself. But see, zero number of harmonic. Yeah. Here. This row. Fourier synthesis. But there is one problem. You see that the problem, I don't have omega time values. Here will be x values. It's okay. Here will be x values, it's okay, but I have tiny problem. I don't have values of omega t. That's mean what can I do? Okay. Equals to I will help myself a bit. Oh yeah. Unexpected end of file. Oh yeah, line 41. Why? Let's go. Oh! Look what I got. It's something, yeah? There is two lines. You see? Two lines. One with crosses and one with dots. Blue line with crosses with plus signs is a result of Fourier synthesis. Points are elements of table of my signal. I can also, okay, I will allow to draw line. From the outside quite good. If I enlarge, see, points, original circles, and pluses, results of synthesis. Best point of view is here. Hey, come on. Oh! Here is a computation point. Again, you see what Fourier oscillates around. Not so hard as a rectangle, but you can see this overshot and undershot and again overshot. And here is the difference. For example, to make sorry. Let's try to increase number of harmonics. From 25, let's say 50. Can we do 50? Bit better, isn't it? I can try to make it more. Oh, this one's cool. Machine, do it. 250. There is a big difference. It's very nice. 350. Takes a time to calculate. Very nice. Okay. 100 is enough. Clear means purge all arrays. So, what would you say? Do I perform Fourier transform correctly? Green line, original signal, blue line, results of Fourier transform. Decomposition and synthesis back appears to be nice, acceptable. Now it's time for much more complex task. Now it's time for much more tricky. For each component, I need to solve my network. First, I will start with AC parts. I need to somehow translate these schematics into something in machine language. What kind of language understand machines? Code matrix. Matrix is a good always. I need to represent this network as a matrix. And first thing I do, I need to set numbers for nodes and branches. This will be node 1, this can be node 2, and this can be node 3. I set nodes at the points where I can measure voltage, where it will be possible to attach a scope. Ground, base node, do not need a number. Also, I need to set numbers to a branch. This will be 3. This can be number 4. Okay, this will be number 5, and this can be number 6. I need to set numbers and, that's not all, directions. Without it, nothing works. Now I can conduct one very specific matrix. It's called first matrix of incidence. Row numbers are nodes, column numbers are branched. If branch in falls into node, you write -1. If it falls out of node, you write 1. In no connection, you should write 0. I will call it. It's also can be known as A or gamma. Like this. It's a straight row. In falls -1. So I have nodes 1, 2, 3 and branch 1, 2, 3, 4, 5 and 6. First matrix of incidence. First branch in falls in node 1. Second branch out falls from node 1. Branch number 3, 1, 2. Out falls, in falls. Branch number 4, from 2 to base node. 1, 0, 0. Branch 5, from ground into node 3. And this one, 1, 0, 0. Here is my matrix of incidence. It describes network topology. -1, 1, 1, 0, 0, 0, 0, 0, -1, 1, 0, 0, and the other one, 2 zeros, 2 more zeros, -1, 1. I will not left it like this. I will use my computing environment to make it more comfortable. Is it clear how did I create this matrix? Nice matrix, but this matrix do not contain resistance. Also, I don't have any EMF sources. Actually, this matrix is a Kirchhoff's current law. But now, what I'm doing, I will need resistance and I will need EMF. For each ideal component, for each harmonic, we will have own resistance or EMF. What's the frequency? 300 Hertz, yeah? F equals to 300. Now, what's this? K from 1 to I will need to perform my calculus for K1 base frequency, K2 second harmonics, K3 third harmonics, and so on. For each harmonics, I will define a variable. It's actually it's J omega. Complex K multiplied by F multiplied T 2 and multiplied by P 1 second 0. What did I wrote? Angular frequency W2PF, yeah? Yeah. At second it will be double, at third it will be triple, and so on. I use complex function to write not omega, J omega. Why I need it? 1 second. I will create here a matrix of branch resistance. First, I will use small vector. I need to do the following task, not to kill myself. I need to fill a special matrix. Main diagonal of forms branches self-impedance. For resistance it will be R. For coil, J omega. And for capacitors, 1 divided by J omega C. Yeah, it's from electrotechnics theory. But that's not all. It's a main diagonal. Also, I have what here? Mutual inductance. For mutual inductance, I will need elements. For example, if I have mutual inductance between branch 1 and 2, this means what elements 1, 2, and 2, 1 will be your omega. Mutual inductance. So first I start from the main diagonal. What I have in the branch 1? 20.35 active ohms. Yeah? Yeah. Plus J omega multiplied by 100 millihenry, it's 0.1 Henry. Do you understand what I'm doing? R plus J omega A. For the second branch, 1 divided by 5A minus 6 multiplied by J omega. Capacitance in microfarads. For the branch 3, what I'm writing? Self parameters of branch, it's 6.47 ohms plus J omega multiplied by 9.3 A minus 3 Henry. 9.3 millihenry. Next one, branch 4. See, 220. Yes, it's 220 ohms. 220. Branch 5. 7.6 plus your omega multiplied by 32 points. 53 A minus 3. It will be inductance in millihenries. And last one, 600. Do you understood what I done? Really? I have branched in sequence, one by one. For each branch, I'm writing real and imaginary part. I can, in this environment, I can write the, because I can use much terms in array definition, I write real part plus J omega, complex frequency multiplied by reactive part. For coil, J omega A, for capacitor 1 divided by J omega C. This vector, this row, is a self parameters of the branches. Look what I'm doing. Next step, matrix is a diag of. After this diag operator, I will get matrix 0, 0, 0s and one diagonal with one branch. Now, I have coupling between branch 3 and branch 5. So 5.3 equals to J omega multiplied by 10 A minus 3. You notice IEEE notation, A minus 3. This means multiplied by 10 power minus 3. 3 digits. Yeah. And the same 3.5 equals, because magnetic coupling is symmetrical. After this, what will get at each fourth cycle will count 1, 2, 3, 4. Yeah. For each, I will get my own matrix. If I double the frequency, reactive resistance of coil doubles and of capacitors reduced by half. Yeah. 3 triples and reduce inductance of capacitor will be 1/3 and so on. From this point I will get matrix of resistance for each harmonic in AC mode. A vector. It's a vector of EMF. I have EMF only in third branch. It will be C K complex of minus small complex means create a complex number. How many and other one tiny moon do I have? Oh, this one. I will use this one and this one too. I will need it. It just takes size of a matrix, and I will need transposed, so I used it. 1 second. A is 0. Oh, demon. Of this 0.1. So, will it work? Wait 1 second. 1.2. Oh, zeros. I'm always it's my problem. Zeros. Whoa, this one works fine, I think. I first see that I need to specify AMF for each branch, but I will have AMF only in branch 1. So 1. I need check. Of course it will not work. This will work. $156. What's at $156? Oh, of course. Copy from different environment. Mm-hmm. 156. One more problem. I hope now it works. Oh, 57. Of course. Of course, it was stupid. Yeah, now fine, this will work. Let's go forward. Now I need a solution, but before I can perform a solution, to solve the system, I will implement a nodal admittance, technique of nodal admittance. Nodal admittance says that I can solve a network as solving equation it's a system of linear equations. This one is for current source. In our case it will be 0. This one is a nodal admittance matrix. M transpose. Nodal admittance matrix. Technique of nodal admittance in matrix form. You have it in previous semester, nodal admittance. Or technique of nodal potential. Yeah, it's the same. It's based on nodal admittance matrix. To solve system of nodal this one is called it nodal admittance, nodal voltage technique. No problem, I need nodal admittance matrix. And to get nodal admittance matrix, I need inversion of resistance matrix. I have problem. I have two non-diagonal elements. But I can help myself with this one. I have a special tiny function allowing me to solve I can solve matrix inversion problem with a technique of Jordan exclusion. So here Z1 is Jordan of, and nodal admittance matrix will be M multiplied by Z1 and multiplied by transposed, by M transposed. Let's check it works. How can I check what I correctly inverted matrix? Oh yeah, don't know that one. Oops, this is stupid. Keyboard not working. If I multiply one, great. 1, 1, yeah, fine. If I multiply inverse matrix with its original, I should get unity matrix. I got something very close to unity. Now I need to solve system of equation. To solve system of equation, I need to solve system of equation to get nodal voltages. More function for the gut function, yeah? I will try to use iterative technique. Technique of sequence. Here. Technique of sequence approximation. Yep. So I need to what? What will be actual network is described by equation system A multiplied by X equals to B. What's B in my case? In my case, it's M multiplied by 1 and multiplied by E. And okay, voltages. I need to pack somehow my voltages. I need to pack my voltages. Yes, that's what I will do. I will use this. I will reuse my code, but I will I will get a vector of voltages per frequency. Let's check what will happen. This one, it's an Ohm law written. It's to get branch currents. There is that in Latvia. This is vector of branch currents. I will create a matrix. First column for first harmonic, second harmonic for second, and so on. Filled with voltages, and same for currents. Oh yeah. Should be hate to do so, but I will. For number 2, not a number. That's not good. I hate this moment. First 0, not a number. 4, not a number. That's not good. This calls internal Gauss solution. This is called for. Can I speed up process? I will return to more precise solution. Got voltages. Do have voltages. Okay. Zeros. Number 4. Got voltages. Number 6. Got voltages. Number 8. Got voltages. Number 9, nothing. 0, got voltages. Works. 12, something. Yeah, it works. I got set of voltages and branch currents. All fine with it, except what's missing? I have all AC modes, but I don't have my DC mode. I need to solve my DC. Now you see a crime. Don't show this to your professor of electrotechnics theory. I will solve DC mode as a very as a very slow AC mode. It's a crime, but not a huge crime. I did it because I'm lazy and I don't want to create. See, in DC mode, I should exclude all capacitors, naturally. I should exclude all coils. Remaining, I should left only active resistance of winding. It's a work I don't like to waste the time. Hey, problem, this will create its own network schematics, own topology. And I will need to keep correspondence table, which branch in DC mode corresponds to which branch in AC. I'll do it brutally. One second. Oh, this is missing. This is wrong. Stop. Stop, 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 stop. This will not work. This will work. And this will work. I don't need this at all. Mm. 16 volts, and we have peak of 14 point. No, should be. Hey, wait 1 second. Wait a second. Fourier this way. Voltage. Okay. 8.26, it's correct. And here are my DC branch currents. Now I have how many? 24. It's okay. I have 24 AC voltages, and number 25 is my DC component. Tiny work, synthesis. Okay, now it's time to get time variables. Time to perform inverse Fourier transform to get time values. I think I can reuse this code or not. How many voltages do I have? 1, 2, 3. And 5 by 2 will be 10, no, nothing. Branch currents and my voltages. Voltage at node 1. Voltage at node 1. Voltage at node 1. Voltage at node 1 is a blue line. 5. Offset.
So with my DC component, then volts okay.
Something wrong with my DC component. Sorry, that's tiny mistakes. I should not stop. Where is the zero? Divide by half here or there. I performed division twice. That's why I got here. Is it correct or not? Of course not. OAC mode, DC mode. Well, this one should be eliminated. Oh no. My check my currents. Okay, here are my voltages. Voltage node 1 looks like something sine, but with offset from 7.3 to 9.25.
blue line from this point, what I see 6, and here A. This is signal at node 1. Its sign, it's from. If you trust here, 8.6 to this 0.6 volt, this 0.8 volts. From 6 to 8. And my calculus from 7 looks like double sign, but from 7 to 9. 7 6 to 8.
What I'm doing wrong? in synthesis, or should average point should be 8 at the first node. Here average point is 6. 4.6, 5.8, 7. Calculus show 7. Where is my mistake? I made a mistake somewhere. 1 second. Okay. This 120. This changes nothing. 20. Where is my mistake? DC component 4. What's the true DC component? Node 1 point where capacitor is attached. Yes. So this voltage true value 7 volts of DC component at this point. Where is my mistake? Can't be. This appears to be correct. This is correct. Conversion performed fine. This is correct. This means what only point where can be something, it's the last one. 16. And 8.25. 0.25. Here I have 6.7. Active resistance 20.3. Yes, 20.35. Yes. Five AC. Okay. At the output, I should see ICDC component 7.6. Well, should be 8.2. Oh. What I forgot. Direct voltage drop on diodes. It will be 1.2 volts. Here is my difference. I forgot what. Silicon direct voltage fall on diode. 0.6 volts on each. Diodes have voltage drop. Stop.
I forgot voltage drop on diodes. That's mean what 1.2. Okay, it's not. It's not terminal. What I need to see, I need my voltage. So for the node 1, 6.2 lower point, 8.6 higher point. Where is my chart? Oops.
Should be from 6 to
the 1 is now the 2. From 6 to 8.
Direct voltage drop. How can I? Minus 1.2. Will I get correct forever? Yeah. Yeah, I'm near. I have a tiny problem with DC offset. It looks fine. You can compare blue line with the number 1. They are very similar, so we are very close. I near solved network. It's somewhere tiny mistakes in DC offset. No. Okay, medical appointment is medical appointment. I have, wait 1 second, where am I at this point? Yeah, I got solution. Here, between 7 and 9, 2 volts. And here magnitude, blue line. It's now between 6 and 8. Also, AC components are solved correctly. This blue line is this one. But I have I made a small mistake in DC component. True DC component of this voltage is 7 volts. And for at point of my calculus 15.11 demon. Yeah, 15.11 if I divide by half. Yeah, where is the 1/2? Where is? Wait 1 second. Saddle salt. Where is DC regime? DC mode, DC mode, DC mode, DC mode. Here is by half. Oh, come on. 7.55 calculated with the
node 1, 7.3. It's a real node 1. Real node 1 is after the here. 7.25. Calculate 755. Yeah, so I solved network. It will. Effective 761. I solved it. Yeah, I finished. I solved this network. I started to looking for the small difference diodes to have a direct voltage drop. If I have 10 volts at input of rectifier, I need to deduct 0.6 volts for each diode. That means 1.2. There was the difference. I forgot to deduct voltage drop. Diodes to have their own voltage drop. Yes, now it's. Where is the chart? Wait a moment. Do I looking on the previous one? Oh. Voltages. No, listen this. Synthesis voltages. Yes. Final, we will see them now, or I don't know. From 6.7 to 8.4. Here. From 6.6 to 8.8. Yes! Blue line fully corresponds to the voltage at node 1. Here, blue line and voltage at node 2 and voltage in node 3. It's very small. See, it's around 0. And here it is, tiny voltage at node 3. And don't have DC component because transformer. Yes, we solved network. Enough for today. You don't have NFC chip. Okay, I'll do it. I need to go to my office for phone. No problem, I will.
Okay, thank you.
Welcome.